Good afternoon, everyone. My name is Leonardis. I am an associate professor in food science and technology at the University of Molise, in Campobasso. I am fortunate to live in the heart of the Mediterranean, where the olive plant grows, and the people, from centuries, use its products, especially the oil. Today, virgin olive oil is considered widely a superior oil, for its nutritional composition, and typical flavor and taste. In addition, olive tree is very appreciated for its history, for the original landscapes that it draws, and for the high biodiversity. Olive tree gives us the oil, but also the fruits, prepared and consumed in different ways, and the leaves, traditionally used in herbal medicine. Indicatively, olive fruit is composed of water, up to 50%, followed by the oil, from 8 to 22%, and remaining compounds, enclosing the phenols. Phenols that represent around 2 to 3% of olive fruit, only a small part of these pass in the oil, while the major part remain in the waste. Also, the olive leaves contain about 3% phenols on dried matter. Phenols are aromatic secondary metabolites, found typically in the vegetables, in which perform different functions. However, olive phenols are very characteristic and differ from those of other vegetables, for composition, origin, sensory properties, antioxidant and nutraceutical effects. Typical olive phenols are the phenolic alcohols, hydroxytyrosol and tyrosol. These can be found in their free form, or bounded with other, non-aromatic compounds, to form the group of psychoiridoids, that enclose oleuropein and lyxtroside, and other their derivatives. Other typical olive phenols are the verbascoside, ligase, flavonoids and various phenolic acids. About the origin, olive tree products are one of the main food sources of psychoiridoids. Oleuropein compounds are associated with bitter and pungent taste, while hydroxytyrosol, in its free form, is tasteless. It is well known that some phenols, especially the orthodipheols, are radical scavengers, helping to extend the shelf life of oils and fats. As a result, endogenous phenols are natural antioxidant of the virgin olive oil. And they are very efficient antioxidant. In fact, we found peroxide values still low in oils stored up to 6 years. Finally, olive phenols show a positive role in the treatment of several diseases. Indeed, the European Food Safety Authority approved the use of a health claim, stating that olive oil polyphenols contribute to the protection of blood lipid from oxidative stress. In order to achieve this benefit, a daily intake of 5 mg hydroxytyrosol and its derivatives is recommended. It is well known that virgin olive oil is extracted through a mechanical process, carried out at low temperatures, by using a press, as in the traditional system, or a decanter, as in the modern centrifugal system. However, olive oil mills also produce abundant wastes, composed of residual parts of olive fruits, such as skin, pulp, seeds, stone fragments, but especially water. Depending on the oil extraction system, these wastes may be solid or semi-solid pumice, here target as OP, or liquid, the olive wastewaters, here called OW. Other abundant waste are the olive leaves, targeted OL, produced during the tree pruning and olive harvesting. It is estimated that approximately 4 kg wastes are generated during the production of 1 kg oil. These wastes are highly polluting due to their content of organic matters. Especially, the phenols are pollutants difficult to treat. From a linear economy point of view, olive oil is the unique profitable product, while depollutio is considered the primary solution for the wastes. Now, we know that this approach is ecologically, and economically, unsustainable. And a circular economy approach is strongly encouraged. In this approach, olive wastes, with also the phenols, should be seen as secondary raw materials for new profitable products. Really, many potential uses are proposed in a variety of sectors. Pumice, for example, can be used in agriculture to enhance soil fertility or to integrate animal feed. Another promising application is the production of removable energy, either as direct fuel or in the form of biogas. However, utilizatio that more interest us is that in the food industry, for the production of pumice olive oil, ingredients, sauces, supplements, novel foods, and others. In this contest, I will present some study cases, including the production of antioxidant additives, vinegar, and functional drinks. Let's begin with the production of antioxidant additives. Actually, there is a rich literature on this topic, and various methods have been tested and validated for recovering the phenols. Furthermore, European Union recently approved the addition of pure hydroxytyrosol in fish and seed oils and spreads. In the laboratory, we use racemiat to test the effectiveness of antioxidant substances. Operating under high temperature and constant airflow, we determine the induction time, in hours, that is a measure of oxidative stability of oil/fat samples. Protection factor is calculated as the ratio between the induction time of sample, with and without the antioxidants. Protection factor hydroxytyrosol, being a autodiphenol, is higher than that tyrosol and related compounds. Like this, not all phenols of the olive wastewaters have the same antioxidant capacity, being many of them are already oxidized. However, we have obtained an extract rich in hydroxytyrosol through liquid extraction with ethyl acetate. This extract revealed high antioxidant capacity, due to it delayed of about 7 times the induction time of a large sample, at the dose of 150 ppm. Olive leaves are also a potential source of antioxidant additives. Nevertheless, olive leaves contain mainly oleuropeae, which shows a lower protection factor than hydroxytyrosol. For this reason, the olive leaves were treated with strong acidic water steam, in order to obtain an extract rich in hydroxytyrosol. Effectively, the extract contained about 2 grams per liter total phenols, of which 92% was hydroxytyrosol. Also, extract confirmed to be a good antioxidant for lard, milk butter, and cod liver oil. We produced, in the laboratory, vinegar from both olive wastewater and leaves, through 2 different processes, fermentation and maceration. In the past as well in present, vinegar is used in different way, especially in food, but also, as detergent, disinfectant, and folk medicine. Many studies have confirmed health effect of certain vinegars, by identifying also their bioactive components. Therefore, the interest in vinegar remains forever high, including the production of novel vinegars from food industry byproducts, such as vegetables and fruits scraps. We used olive wastewater taken from a local traditional olive oil mill. The wastewater was, preliminarily, diluted 1.5 times with water, and supplemented with 10% sucrose. Treated wastewaters were split in 2 parts, leaving a 50% head space in their containers. 2 types of fermentation were carried out. In one, commercial yeast starters were inoculated, while in the other, spontaneous acetification occurred. After 5 months, when acidity stabilized at 4%, the vinegars were filtered, analyzed, bottled, and properly stored. These appeared clear, with a vinous red color, and without any abnormal smells. Procedure to produce olive leaf vinegar was simpler. The air-dried leaves were homologized with alcoholic vinegar with a 18% acidity. Homologate was left to macerate for 15 days. Thus, the vinegar was filtered, analyzed, and bottled. Also in this case, resulted vinegar appeared red-colored, clear, and without any unusual odor. Starting characteristics of all olive vinegars remained the same, even after a year of storage. pH and total acidity unchanged, indicating a good stability of the products. Total phenols were about 4 grams per liter on average, evidencing the functional potential of the vinegars. In fact, just a few ml of them meets the recommended daily dose of hydroxytyrosol. In addition, HPLC analysis evidenced, in every vinegar, an increase of hydroxytyrosol and its derivatives during the storage. Finally, we also explored the possibility to produce a beverage from two-phase pumice. Recently, it is growing strongly the demand of functional drinks, which claim the presence of natural or added bioactive components, such as vitamins, proteins, amino acids, minerals and others. For the preparation of olive drinks, the pumice was diluted about 2 times with 2 liquid ingredients, 6% citric acid or water. 2 extraction systems, ultrasound or heating, were carried out. And finally, 3 different treatment times were applied. All beverages were centrifuged, filtered and analyzed. At the end, homologous samples, resulting similar, were combined to create 4 different final beverages. All drinks contain high value of total phenols, around 500 to 700 mg per liter on average, especially in the form of eau-de-fiols. HPLC analyses revealed a significant presence of both hydroxytyrosol and oleuropi-related compounds. However, the sum of them resulted about 3 times higher in the citric acid drinks than water drinks, with further significant loss due to the ultrasound treatment. However, also in this case, functional potential was evident. In fact, a small glass of citric acid drink can meet the recommended daily dose of hydroxytyrosol. In conclusion, also these mentioned studies confirm the potential benefits that could derive by recycling olive oil mill byproducts in the food industry. Thank you very much for your kind attention.